So we're very happy to have Graham Farmelo visiting here today. He's a noted biographer and science writer, and I know one thing that I always wonder when I'm reading books about science or scientists that are aimed at a popular audiences, does this person actually understand the science, or do they simply understand the story? So Graham trained as a physicist and as a theoretical particle physicist. He got his PhD in 1977 and then was a lecturer at the Open University in physics until 1990, after which he moved into his second career as a science communicator and science author. He is very well known for writing what is, I can make the statement that I consider the authoritative biography of Dirac, The Strangest Man, which many people have probably in this room have read. He's here today to talk about a topic that comes naturally out of thinking about Dirac, which is the role that mathematical beauty plays in the development of physics. But he has also authored a book about Britain's role in the development of the atomic bomb. And he's currently, I just learned today, writing the authorized biography of Stephen Hawking. So we have something else to look out for. If he's going to be talking today mostly about his book, The Universe Speaks in Numbers, and if anybody is inspired by that, I believe we're going to have copies of it at the reception if you'd like to pick one up. I'll just make that plug since Graham probably won't. With that, we're very happy to have him here, and yes, happy to have you.
Thank you very much indeed. Thanks to you and to Josh for inviting me and enabling me to speak this afternoon. It's really great to be here. I pity those of you that have had a double or even triple dose of me today. It was unintentional to give you quite such a concentration of my of what I have to offer. But anyway, you're very welcome, and I'm delighted you're taking the time to come this afternoon. What I'm talking about this afternoon is this remarkable relationship between physics and mathematics. Very important to bear in mind, something that is often got wrong by people in the public, understandably. That is that physics and mathematics are actually different subjects. We know, I bet everyone here knows, that they are actually very, very closely linked, with links that introduce great thinkers to talk about miracles, eternal mysteries, and what have you. Please come in and come on this side, please. The most arresting description I know of that relationship, for those of you who have a slightly prudish disposition may need to look away now, but the great mathematician and also distinguished thinker about physics, Hermann Weyl, wrote in 1928 that face-to-face mathematics and physics disdain one another. In the dark, they fertilize each other. That's a quote, and that's a book from his great text on group theory. Remember, he and Eugene Wigner wrote these books that brought that aspect of study of symmetries squarely into the study of physics. And although I'm not going to be talking in detail about Weyl, he's one of the people who really did excel in both of those subjects and wrote brilliantly about their relationship. Weyl's friend, Albert Einstein, made I think a brilliant, simple contribution to this subject, which I don't think is discussed often enough among physicists. Right? The wonder of our subject and its relation to mathematics. In March 1952, when Einstein was just 3 years before his death, he didn't know that, but he knew he wasn't in the greatest. Please come and get a seat. I mean, I feel really bad. There's seats here. And he wrote that the essential miracle of the universe that he saw, and he did say, in brackets, or eternal mystery, is that the universe is fundamentally ordered. Right? That is what makes science possible. That the universe that we find ourselves in here is something that is amenable to observation and to laws of, we call them the laws of physics. This is what enables us to do things like make measurements and observations. And as James Clerk Maxwell will come on to later, just making measurements and observations isn't actually that interesting. What is really interesting is that those observations can be correlated in terms of those laws. Those are the patterns that Einstein was referring to. Maxwell wrote brilliantly on that. He's someone who was an expert theoretician and an expert experimenter. That presence of patterns of order in the universe, that is where the link with mathematics comes. The great mathematician G.H. Hardy wrote in his wonderful book, The Mathematician's Apology, that mathematics is fundamentally the study of patterns of ideas, enduring patterns of ideas. Patterns is the key word, and that's where they link. The patterns of ideas that mathematicians work with, and the patterns of laws that the physicists use. And you'll know that those two subjects are linked by their common common focus on order. When did we first know that that those subjects were linked? Well, you can, like almost everything else in intellectual endeavour, you can go back to the ancient Greeks. So great, that's what I'm going to do in my retirement, because I've told you can learn most things from footnotes to Plato and what have you. And I don't want in any way to demean the fantastic work they did when they were teaching Europeans how to think, basically. But I want to jump straight off to a summer Saturday in 1687, in which almost nothing happened. I can tell you that because I've made a really close study with researchers of anything that happened on that day. And one thing happened, right? This book was published, right? This is the Principia Mathematica, written by Isaac Newton, published on that summer Saturday, a print run of several thousand, which struggled to sell out. This, in Einstein's description, accurate description, was the first working system of theoretical physics. That is accurate. It is not accurate, and Einstein knew this, he was far too smart not to know this. Newton was not a theoretical physicist. He wouldn't have known what you meant by that, probably. He might have obviously smart enough to work it out if you talked to him long enough, but he regarded himself as a natural philosopher. He also regarded himself as a mathematician. By the word natural philosopher, I mean that Newton saw his role, right, brilliantly set out in the fantastic book Priest of Nature, which I warmly recommend to you, by Rob Iliff. That book shows that overwhelmingly the most important thing in Newton's life was that he regarded himself as a servant of God. The universe for him was self-evidently the work of all-powerful, all-logical, all-good, divine entity that he called God. And he regarded his job as to study the order at the heart of this universe, as we call it, everything that exists. In this book, he stood, as we know the phrase, that's actually in Chartres Cathedral, it's not Newton's, most people think it is, right? He stood on the shoulders of giants, and he was standing on the shoulders of Galileo, Kepler, and indeed the ancient Greeks, the people he revered most. And he set out a scheme that virtually everyone here takes for granted. It's so obvious we don't even think about it, really. Namely, that if you want to understand the universe at a fundamental level, what you do is you set out your laws in mathematical form, but with those variables having complete specificity and generality, and you compare the predictions, the statements about the universe, to the most accurate measurements that you can muster, and that if they disagree, you go back to the theory and you modify it until you get a better description of God's universe. And in that way, you get this, we can appreciate the masterful way in which God made the universe. Now,
I ask a question? But
Sure.
But was that the first? But was he the first? I mean, that's not where you're first getting this idea? Was it coming before him? Is he getting this?
No, he did. I would have to give a separate talk to talk about the different strands, right? But Newton took those ideas from the whole group of people, right? From Kepler wrote that God is a mathematician, Galileo wrote basic laws of kinematics, but he didn't, for example, use the term law of nature, which is what Newton took. In fact, that was first written by Descartes, who was very important view. We could be here literally all afternoon talking about the influences of Newton, and it is a worthwhile question you ask, especially because I'm English, I'm not suggesting that he did everything, right? But what he did was he pulled the system together, right, in a way that constituted, as Einstein wisely said, the first working system. And you know what it did, right? He could, he had a unified view of gravity. The thing that pulls an apple to the ground also holds the Earth in orbit around the Sun. It also used to predict the path of the planets. It predicts the path of satellites. You could predict tides. You know, all these wonderful things. And the thing that really distinguished Newton from Galileo, and I got this from the great Simon Schaffer, one of my favourite historian of science in the world, is Newton's completely unswerving determination to check always against data. He organised the first global initiative into gravity research, right, in order to check that Newton's law of gravity, right, with the universal law is correct. In other words, he really did follow that. Now, Galileo would never have done that. Right? So he really took these things to a new level, so to speak. But I don't suggest that he invented it all on his own. Very important thing. Newton, for many centuries, has been seen as a byword for genius. I never use the word genius except now, because it's a lazy term. But I mean, if anybody deserves it, in my opinion, it's him. But it's important. No matter how accomplished you are, right, in science, you never finish. And Newton did not finish his program of gravity. He couldn't do. He screwed up some of the calculations. Sorry to be disrespectful. Right, the moon's motion of Neptune. That he could never finish the calculation of the tides. He didn't have enough mathematical firepower, even though, of course, he was a preeminently brilliant mathematician. So he knew that he hadn't completed the project. He knew that he hadn't got the mathematical laws of electricity and magnetism, for example. He knew about the phenomena, but it was a completely different matter to actually find those laws, which he couldn't do. Don't in any way wish to diminish what he did. I'm just saying it's a complicated and very, very demanding subject. What it did do is establish that you could use what became known as the torch of mathematics to shine a light on the makings of the universe. This is what I'm going to be seeking to do today. First of all, having talked about the torch of mathematics with Newton, to look in the earliest 20th century on how we came to focus on the mathematics of fundamental theories, the way mathematics and physics drew apart, surprisingly, after the Second World War, but got back together again with the pulling together, brilliant jamming together of quantum mechanics and relativity, leading to new physics and new mathematics. This illustrated, I will argue, a view that mathematics is comparably important to experiment in guiding our way to the future. But we could argue that mathematics is leading physicists astray now, a view that is increasingly popular, and I will make some comments on that. But let me begin almost 150 years ago with one of my very favourite thinkers about the natural world. This is James Clerk Maxwell, and this is fake news. This is a doctored photograph. We have so many of these now in British life, right? But this is a doctored photograph of the great James Clerk Maxwell talking in the Crown Court of Liverpool in 1870, in September. And he was at a public meeting, and he was talking about a subject he said was too grand for him, because he was a very humble guy. He saw himself, rightly so, as a natural philosopher, right? Not as a physicist, natural philosopher. His favourite reading was the Bible. Second favourite reading, Shakespeare. He was there because he was a master in the same way that Newton was, at understanding the world around us, in particular by framing it in mathematical terms. And he made contributions to optics, mechanical structures, heat engines, astronomy, and what have you. Right? He was recognised as one of the most brilliant people of the age. Not the only one, but a brilliant person of the age. What everyone here will, who's studied physics will know that this gentleman, James Clerk Maxwell, did for electromagnetism, in a sense, what Newton did for light. He set out a set of equations, a mathematical description of electricity and magnetism, and how it relates to the ether. That's very important. Most physicists get this wrong, right? For good reason, because they're taught modern perspectives on things. Maxwell was not just thinking about electricity and magnetism, he was thinking about it as a package with the ether, whose existence he was completely confident of. So he produced that theory, which now every student in the world of physics studies, right? Although they study a more modern version of it, which is much more condensed than the one he produced. But he was the progenitor, so to speak, of this thing. One of the things I want to stress about Maxwell was that, brilliant though he was in physics, he was one of the generation who started to get really interested in what for him was modern mathematics. Not just recreationally, he would read about the theory of knots, the theory of projective geometry, of quaternions and what have you, looking for these mathematical developments. Doesn't matter if you know what they are, but they are modern developments that were conceived in pure thought by mathematicians that could work in a darkened room, so to speak, looking for ways in which they could be mapped onto the world to see if there was some pattern that could be established there. Now, Maxwell was asked to go to Liverpool to talk about that relationship between physics and mathematics, and you can find it with actually a little bit of difficulty, but it's not impossible. You can read that monumental lecture. It consists of a lot of jokes. He loved writing poetry, he loved writing jokes. The opening has a joke about quaternions, right, in it. And he talked there about, with great generosity of spirit, about how some physicists are absolutely terrified, right, of mathematical equations, right? Those people very often couldn't, as we would now say, install a plug, right? They have absolutely no ability at all at experiment. And he had a very, very generous view that we need all types, right, in order to understand the world as we see it. And in that lecture, he argued very subtly, and again it rewards multiple rereadings, that there is a place for modern mathematics being brought into physics to help increase our understanding of nature. Now, Maxwell's achievement was only really clear when Hertz discovered something called electromagnetic waves, which Maxwell had argued within the context of his theory absolutely brilliantly. Those waves were in fact light. It was one of the great unifications of modern thinking, where these waves, which Maxwell had tentatively predicted, there's a subtlety there which is written in my book, but it will do for this talk, and those things were discovered by Hertz in Germany after this poor guy died of cancer aged 48, not knowing whether his great theory was the right one. There were other competitors, his turned out to be the right one. Maxwell became better known and even more lauded after his death, which, as I said, took place when he was only 48 years old. And by 1900, we know from Max Born's notes that almost everyone, virtually everyone, accepted that Maxwell's theory, a set of mathematical equations, could be used to describe electricity and magnetism. But not everybody taught that subject. And one of the people who decided to take things into his own hands was this gentleman, Albert Einstein. Now, who doesn't love Einstein? Right? There's so many things to like about Einstein, very few things to dislike. When he went to university, he was bunking off not only maths classes because he didn't think you needed advanced mathematics or significant amounts of advanced mathematics. What you need to do is focus on really important stuff. And he really focused on that Maxwell theory of electromagnetism. That was his obsession. He wrote it several times in his recollection of his life as a student. And most people here will know that this great mind, the person of the century, according to Time magazine, had his greatest triumph perhaps in 1905 when he wrote a small number of papers that were retrospectively, it's obvious, were astonishingly radical contributions to our understanding of the physical world. I'll just mention two. One is the special theory of relativity, which was a modification of Newton's idea of space and time, which Newton had a perfectly defensible but not quite accurate view of space and time as universal things that did not depend on motion. The other one was Einstein's brilliant work on the light quantum, which he saw as he always said was his only truly revolutionary contribution to physics. By 1905, as I said, he was virtually unknown. He was working in a patent office. He was doing this brilliant work, but he still, in a way that astonishes me, he was still in his spare time with two young children doing what we now see in retrospect as the greatest work in theoretical physics at the time. Incidentally, he regarded himself as a theoretical physicist, not a natural philosopher. Let me annoy people by saying, I stand by the view that Einstein was 50% natural philosopher, 50% theoretical physicist. But let's argue about that at reception.
By the way, he wasn't raising the kids alone.
I beg your pardon?
He wasn't raising the kids alone.
No, that's true. That's true. We'll continue this argument later on. You will probably win by the sound of it. But anyway, it's very important, right, though, that he really was maths averse. I'm sure you've got students like this, and we should be sympathetic to it. Why would you need complicated mathematics to understand the world? That was his very strong view. And everything he wrote in those classic papers, you could do with maths that Laplace, in particular, who led the completion of that Newton program. Laplace could have used just that mathematics, which was 100 years old. He didn't see why he should learn all this fancy stuff that was coming out of European centres in Petersburg and Berlin and other places. But around the time this picture was taken in 1912, he was working almost full-time, not in developing quantum theory, which was seen as a very, very pressing problem at the time, but he was focusing on another of his grand projets, which is to produce a brand new theory of gravity. This was he saw as a generalization of Einstein's special theory of relativity. He believed that using a theory analogous to Maxwell's, what we call a field theory, that we needed a field theory of gravity that would supersede Newton's. But he was damned if he could work out how to take things forward. Everything changed when he was introduced by one of his college mates to the theory of curved spaces, which had been invented by Gauss and Riemann and Christoffel and others. This was a revelation to him. That mathematics, I'm not certain of this, but I'm almost certain. I don't think he'd even heard of it before then. Right? He certainly would have avoided classes on it as an undergraduate. This was what he would call fancy mathematics. He then called it, quote, a pure luxury for physics, but he found he had to use that mathematics if he were to realise the physical principles that he was basing his theory on. For experts, the principle of equivalence and the principle of general covariance as it became known. And this is the key thing. Einstein saw this mathematics. It was like a golden key that mathematicians had left on his side, right? That once he had that mathematical system, right, that pattern form, this enabled him, right, to set out, right, it was not easy, it was very difficult to do, but it enabled him to have a framework that facilitated the setting up of what later became the general theory of relativity. It's worth stressing that Einstein began this project in 1907. He didn't finish it until November 1915. So it was 1912, right, that he had this mathematical epiphany, so to speak. And it's very important to remember also that for Einstein, who was not a great mathematician, that is not being disrespectful, he would be the first to say that, he struggled to do advanced mathematics, right? But he was an absolutely brilliant theoretical physicist, absolutely no question about that, a deep philosophical thinker as well, fantastic intuition, but he was a real struggle for him, right, to do advanced mathematics. But he did it, and with a huge struggle that now makes mathematicians wonder. I know people that have looked at his papers and wonder what on earth he was doing, because he was struggling so hard with that subject. In the summer of 1915, he took his almost finished, but not finished, theory of gravity to the burgomasters of Göttingen, which included David Hilbert. I stress again, an unfinished theory. It's quite, you read the papers of their gossip, they said, this guy, brilliant physicist, he doesn't know what he's doing in mathematics. So Hilbert, arguably the world's greatest mathematician, decided, I'm going to go in for that, right? And Einstein found himself in the late fall in a head-to-head with arguably the world's leading mathematician, right? Not a good physicist, Hilbert, but he was a superb mathematician. And Einstein was quite clearly terrified, just as you would be, right, if you'd laid 7/8 of a golden egg, right, that he would be beaten to the post by Hilbert. And Einstein just beat him, just by a few days. It was actually a matter of academic dispute for a time. Now, what delivered Einstein to that? Well, in Einstein's view, and I'm careful to say that, right, what delivered him was mathematics. It was what he regarded as the most natural form of the tensor formulation that steered him to those final equations that he announced to the Prussian Academy, a brand new law of nature. That changed him. He believed, right, that mathematics was holding his hand and delivered him to what was, I think, most people see as his greatest triumph. This. Some people would say that this actually corrupted Einstein in some sense, right? Because after that time, after the exhausting challenge of finalizing the equations of gravity, he drifted towards a much more mathematical approach to doing theoretical physics, where instead of looking at experiment to deliver him, right, he was looking at mathematics to form the guide. What was he working on? Well, he had a theory of gravity, he had his hero Maxwell's theory of electromagnetism, and he wanted, like all generalizers, to form a theory that went across all those forces. He wanted a unified field theory of electricity, magnetism, gravity. And he believed that in the absence of experimental clues, that mathematics would lead him to success. Problem was that people thought he was unhinged. On Saturday, 10th of June 1933, quite some way after that, he started to work full-time on this unified field theory in the mid-20s, when other people were working on quantum mechanics. He gave a talk here at Rhodes House in Oxford, where what he said will have stunned the audience. He told them, and again it's an article you can read, no problem, I don't think there's any mathematics in it at all actually. He said that the method of theoretical physics, not a method, the method of theoretical physics was to use the creative principle of developing the mathematics within a theory. Now this was seen, let me be really clear, as an extremely unusual way to do theoretical physics. The way that I bet almost everyone here, if not everyone here, looks to do theoretical physics is to look at what nature is telling you through the observations and measurements, to take your stimulus from that. And the overwhelming majority of theoreticians did it in that way. Einstein was taking a lonely and very different path. And at the same time, he abjured quantum mechanics, which he found unsatisfactory, respected its predictive ability, but he steered clear of that. Hence Einstein from actually before this time, before 1933, which is when he came to America, incidentally, just a few months after this, was seen as a semi-detached figure doing physics in a way that most people thought was doomed to failure. Just a couple of questions. It's always good to go to Wolfgang Pauli for the rudest comments on his comments. So I'm going to give you two just to entertain you. Pauli was much younger than Einstein, a brilliant physicist, no question. He wrote to Einstein and said the classical field theory was a completely squeezed out lemon, right? And he basically accused Einstein of being something similar, basically, of attempting to use this completely wrong scheme for making advances. He also accused Einstein of having switched to pure mathematics, right? And Einstein really was extremely dismissive. He just laughed and said, well, nonsense, basically. And just carried on with, you could say, commendable stubbornness, you could say foolishness. It's up to you, but certainly with integrity. He found himself around. He had found himself in the 20s and certainly by the 30s among what you might call the new kids on the block. This was a picture of the Solvay conference. I think it was 1927, right, where you have the undisputed monarch in the middle. Somebody who obviously wanted to be the undisputed monarch, Paul Dirac, who was just for Dirac connoisseurs, sent a picture of that to his department in Bristol. And Dirac was the most modest of people. He knew what he was doing, right? And here you have all these great people. You have Planck, you have Lorentz, you have Compton, there's Heisenberg is here somewhere, and Schrödinger, Ehrenfest. These were the people that were fashioning the most revolutionary theory of the 20th century, much more revolutionary, as Einstein would be the first to say, than general relativity, a complete break, so to speak, from Newton's view. That theory was quantum mechanics. The idea that and this is began with Planck's brilliant observation that the energy transfer between radiation and solid matter, right, happens in quanta. It doesn't happen in any amounts, right? It's rather like sugar. It doesn't come in a continuous stream. It comes in lumps. And quantum mechanics was a generalization of that to a theory of motion on the small scale, which was really quite unlike what Newton would have seen. Newton would have been amazed to have seen that. Whereas Newton, to quote my friend Michael Atiyah, would have taken about an hour's tutorial to understand general theory of relativity. Right? So quantum mechanics really was quite something. Now I want to concentrate on one particular member of that quantum mechanics community. Now, you won't be surprised to know that that person is Paul Dirac. Now, I'm not here to suggest he was the greatest of those people, but I am going to assert something that I think is undeniable, that he was the most mathematically minded of those quantum mechanical pioneers. Over and over again, when Dirac was elucidating this theory of motion at a small level, Dirac would have come up against new mathematics. Remember, Einstein had done that when he did his gravity theory. He'd come across the theory of curved spaces. With Dirac, he came across a thing called non-computation, right, straight away. Right? He found that when he read Heisenberg's first paper, that the order in which you multiply these things called operators in quantum mechanics actually depends on the order on which you multiply them. Everyone knows that 6 times 7 is the same as 7 times 6, 9 times 10 is the same as 10 times 9. Right? When the order actually matters, that is mind-boggling, and that was the thing that worried Heisenberg. But Dirac had seen that before with the theory of quaternions in projective geometry, and found himself innovating on one of what Atiyah established as one of the principal themes of 20th century mathematics. When Dirac, a few months after this talk, produced the first quantum theoretical description of the electron, he found himself working on things called spinors, which were right at the frontiers of pure mathematics. After that, he produced a theory of the magnetic monopole, which projected him by looking into these putative objects, right, put him right onto the into the path of people that were working on contemporary topology. Right. that because he introduced geometry into the quantum mechanical description of the world in that thing. So Dirac over and over again found himself right on the same territory as mathematicians, and this put the ideas into his head, as you can imagine. And it was in 1939, just before the outbreak of the Second World War. More fake news. This is Dirac, putting of Dirac picture in front of the Royal Society of Edinburgh, where he gave a talk on the relationship between math and physics. 1939. By this time, Dirac's golden years were over. There's no question that they established him for all time as in the pantheon of physicists, but he was very disillusioned by the state of physics at this time, and he said later on that he wanted just to think, what do we really know? How can we really make progress in physics? And this was where, as Neil mentioned earlier, he came out with his principle of mathematical beauty. This is actually quite easily stated, although he doesn't actually do that in words of one syllable in the paper, although I'm absolutely certain he won't disagree with what I'm about to say. He believed that when you set out fundamental theories of nature, that they advance using more and more beautiful mathematics. He believed that was true of mechanics, of quantum theory, of relativity. And he believed that mathematical beauty was a lodestar, right? That physicists could look to. They could say that the future theories we're going to be developing here will have beautiful mathematics in them. And this led to what some physicists quite clearly thought was crazy, that rather than look at experimental data, you could actually look at beautiful mathematics and then conjecture that it might be useful. Now, that is still a very controversial thesis, but Dirac absolutely believed in it, believe me, without any qualification at all. Let me say, if you don't like the language of beauty, and he never defines it, and he was conscious of that, and I think he was rightly criticised for taking such a subjective notion and making it central. Let me quote something that I said this lunchtime, because I still love these sentences, right? He said in this virtuoso lecture, right, that mathematics is a game in which mathematicians invent the rules. Physics is a game where nature provides you with the rules. What is astonishing is that the rules that mathematicians find interesting appear to be the ones that nature has chosen. Right? No mathematics in that, but what he's saying, he doesn't use the word beauty there, but what he is saying is how we can use mathematical insight to understand the world by looking ahead to what theories might come in the future. Let me be really clear. Towards the end of his life, he said that the principle of mathematical beauty was almost a religion. That is a direct quote from him. Let's just take those quotes. I may have actually in my... There we are. There we are. I've given you two already, so anxious was I to tell them. This is the key line here. Right? Dirac was, although extremely taciturn, extremely cautious in many ways, he put in that paper that he thought that physics and mathematics may one day unify. Very, very strong statement, not the sort of thing that you would regard as a cowardly statement about the future of physics. Now, it has to be said, after the war, mathematics and physics were certainly not unified. Freeman Dyson has stressed to me, and has many others, right, including Michael Atiyah and others we'll come to, that mathematics and physics had no real need to each other. It was almost like they divorced. They could get on very happily on their own. Mathematicians working on the scheme set out by the French, the Bourbaki movement, which really disdained practical applications and just looked at the axioms of mathematics and the idea of setting things out in an ever more precise and logical form. Physicists, on the other hand, were making actually quite good progress, right, with using really not very fancy mathematics. And as Freeman has said, he has a great quote from when he was being taught mathematics during the war, that advanced mathematics was described by physicists as a French disease. I love that. Especially when you know that French disease is synonymous for venereal disease. I didn't know that. But that's their contempt, right, for fancy mathematics. Freeman, still alive of course, still going great, was a very, very good mathematician. Very fine, and they knew that. He saw an opening, right? He's told me this many times. These physicists are really amateurs in mathematics, and he went into that subject and he cleaned up by being one of the major architects of quantum electrodynamics. I want to mention another witness to that divorce, the great Karen Uhlenbeck, and she confirmed to me very strongly, she'd been older than Freeman, about 15 years younger, that the atmosphere was starting to change when she was a graduate student, and Karen did some of her most wonderful work mining a type of theory known as gauge theories that yielded so much mathematical interest. So she confirms that there was that divorce, but it was thawing in the 1960s in the company she kept. Now in 1970, this is when I did my. This is not me, incidentally, just so there's no doubt. In the 1970s, a non-entity appeared on the scheme. Me, right, as a humble graduate student going into the world of basic physics, ill-equipped to appreciate what was going to happen, because in the 1970s, which was an awful lot of turmoil in the real world, it was an incredibly exciting world for me, because we had the most astonishing things going on. We had a gauge theory that described for the first time all the forces that hold together atoms. We had advanced mathematics coming out from those theories, right, which looked terribly intimidating to me and I hope would go away. And there was a new coming together of the mathematical and physics community, which I didn't fully understand because it frightened me so much. That's the truth of it, right? I thought physics was about relatively simple mathematics, and that's what my colleagues in my department thought, right? But if you look at what other people were looking at, that wasn't the case. Now, to understand that, it's very important to recognise something really important that's not stressed enough, right? That in what we're talking about in the rest of this talk, we're talking about an astonishing thing, which is two theories: special relativity, the theory of space and time that Einstein put together, developed into the theory of gravity, and quantum mechanics. They are both fantastic pieces of 20th century physics, no question. Now, as Einstein and everybody else knew, but Einstein was very vociferous, the mathematics in which you set out quantum mechanics is very, very different from the mathematics that you set out relativity. And Einstein and many others said it was virtually impossible to imagine how you could bring these two things together. And one of Einstein's responses to that was to say that quantum mechanics is not fundamental, and he put all his energy into developing, building on the theory of relativity. But there's a near miracle. I'm not going to call it a miracle, but Dirac was one of the people who started this, right, and regretted it in many ways. It is just possible to bring those together to form what is called a relativistic quantum field theory, right, of subatomic particles. Brilliantly explained by Stephen Weinberg in his field theory book. It looks so close to being impossible, you wouldn't believe it, but you can just do it. Right? And this seems to show that nature, it may look like these things are completely immiscible, but you can just about jam them together and keep those two very, very different constraints together. And it was that formed the basis of those theories I was talking about in the 1970s. With my current project coming up, I wanted to mention another great triumph of this, which I remember hearing about as a graduate student and going to Dennis Sharma's talk, where he was talking like he'd just been to see the Sermon on the Mount, right? When Hawking brought together quantum mechanics and relativity and produced a new understanding of black holes, right? That is it's going to be seen, in my opinion, as one of the magic things in 20th century, that you had these disparate things that keep producing these incredible insights when you just about you tread that incredibly fine line that enables you to bring them together. Let me just say that theory of gauge theories is, in my opinion, gave rise to the Standard Model, the picture of the mathematical picture that describes atoms at their deepest level. I think that is one of the great cultural achievements of the 20th century. I said it was based fundamentally on quantum mechanics and relativity. I still kick myself for this, right? But what was happening at the edges of this subject, and I think it's fair to say many of the best people, right, was that they saw that in that mathematics of gauge theories were insights that could be developed independently of the new experimental clues, so to speak. And the people who were mining that area were not only first-class theoretical physicists like Gerhard de Hooft, Sasha Polyakov, but also mathematicians like Michael Atiyah, who had done his greatest work in pure mathematics. He would have said that. He died, as you may know, was it just over a year ago, right? But he started to get interested in the mathematical potential of gauge theories and then opened up a whole new volume of material of mathematics. Now, it's worth stressing here that, to me, the most significant collaboration after the Standard Model was achieved its glorious validity in the hands of experimenters who showed that it worked so well, was the combination between a mathematical talent and preeminently a theoretical physicist, Edward Witten. Michael was a great geometer, and he morphed into a quasi-physicist when he began to work closely with Edward Witten, who came off stage from a student of economics and modern languages, came like a firework from outer space into the Princeton University department and became a preeminent physicist with an extraordinary talent for mathematics. They met in Harvard in 1976 in Roman Jakiev's office, where this gentleman here was a junior research fellow at Harvard. This person had never heard of him before. And he said over and over again, no disrespect to other people, he said this guy knew more than anybody else about what was going on. And from there, those two forces initially of a brilliantly accomplished mathematician and a theoretical physicist with an quite extraordinary talent at mathematics were to dominate the field. Right? Some people were not happy with that. They thought they sort of took it in too mathematical a direction. That's not my view, but I just need to say that in fairness. Now, Michael, he gave me the last interview of his life, last November the 1st, not last November, the one before that. And he repeated then one of his favourite analogies that if you're not a physicist, is I think well worth bearing in mind, because I think it's very graphic. That he still wonders at what happened. You had these gauge theorists over here, right? Doing experiments on quarks and leptrons and what have you, and they were busy working on their theory. Over here, you have mathematicians like Michael Atiyah working on theories of fields and what have you. Now, what happened was that these two people were not talking to each other until around that time in the 1970s, and then, as Michael put it, the two tunnels intersected. And he will even say, and who was it said this? Yang, that's right. Yang, I was just reading his book the other day, that those two tunnels can be regarded as intersecting at the University of Oxford in 1977, when Witten was in Oxford. Roger Penrose was there. There were a whole bunch of very it's not just those people. I don't want to imply that it was just those two people, but got together and they really started to develop the quantum theory of fields. And I love that image of how you could think they had nothing to do with each other. And the tales I told many of them in my book are remarkable because they were finding connections they did not know existed. It was a bit like one group speaking Russian, one speaking English, and then finding that they had overlapping interests that matched perfectly. Michael said, again, this was how many days before he died? 15. He said this was the most remarkable thing in terms of interdisciplinary study he'd ever seen in his life. So, what has that given rise to? Well, the thing that I wanted to stress, and this is a colossal industry, incidentally, but I describe these examples, I hope, accessibly in my book, is this realization that as Eugene Wigner, that's Dirac's brother-in-law, very fine physicist, said that the utility of mathematics in physics is unreasonable. It just is. How can it be so? How can mathematics be so effective in physics? In recent years, we've discovered that is only one side of the coin. The other side of the coin is that physics is incredibly useful in mathematics. Mathematics, right? Physics is useful because it provides people like Michael Atiyah and Pierre Deligne with the intuition that enables them to develop their abstract ideas. Now, this, ladies and gentlemen, I think is a truly remarkable thing. And for those people who are experts in it, it gives a very strong feeling, and I know that's not the same as empirical evidence, but a very strong feeling that there are some forces in there, right, that are driving those two subjects together. Right? If you ask me, and somebody's going to ask me this later on, right, so I'll answer it now, why? Why are those two things? I do not know. I have asked Witten and Atiyah, and I've asked lots of others, why is mathematics so useful in physics? Why? And they say, basically, I don't know. Or they might offer you a hint. They say, don't put that in your book because it might be rubbish. Right? In other words, it's almost a mystical thing. I'm not trying to be mystical myself, but there is no clear logical reason why those two things are so, and that's why I think Einstein was correct to use that word miraculous. Now, just to get examples for the experts, the sort of thing I'm talking about here. In quantum field theory, monopoles, instantons, and the incredible flowering of algebraic geometry. That was in the 1970s and continues to this day. The amazing discovery made by Simon Donaldson, Atiyah's student, about what Michael said. It's not my view. My view doesn't count. What he thought was the greatest piece of mathematics done in the last 50 years. And that was done when Simon Donaldson was building on the mathematics of gauge theories, right? Taken from physics, and he came up with these astonishing discoveries about four-dimensional manifolds. I was in the room when I went to see Simon, and in Dirac's lecture in 1939, he says, you can go and read it this afternoon, I think you will see that four-dimensional spaces are going to be of particular interest to mathematicians, because that's the space in which our universe is built. And I remember looking at the face of Simon Donaldson, right? This was, 3 years ago, right? And seeing that Dirac had alluded to four-dimensional manifolds are special, and mathematicians will find that. And he was the person who, more than anyone, it's an industry, had struck gold in making that discovery. In the last few years, the friend of Neil and myself, Nimar Hamed, and his colleagues have found that the scattering amplitudes, the amplitudes that describe the scattering of gluons, fundamental particles with no shape or size, if you look, basically it's one step up from nothingness. But if you look at the mathematics that govern those interactions, you are led to a completely import mathematics done by the great German mathematician Grossmann. Right? And this is a whole new field of scattering amplitude studies. And of course, the thing that Michael described as the biggest goldmine of all for mathematicians, string theory, which began as a generalization of those early gauge theories. These are the fields, and this is only a very, very high altitude summary of where mathematicians now are being propelled to each other's territory. My contention, as I say from the title of the book, my book, The Universe Speaks in Numbers, is that we must get out of our heads the idea that the universe speaks to us only in terms of experimental data. Yes, it is absolutely critical. Yes, for a theory to be a theory of physics, it must be validated by experiment. That is true. But also, I believe, following Dirac and Einstein and a host of others, that we are in a position where by studying those patterns and gradually being guided by ever more patterns that gradually are converging on something that gets closer and closer to truth, that mathematics is helping to guide us to. But There's a lot of people who disagree with this, and they're not fools. They have reasonable grounds for doubt. I don't think they're right, but I think they need to be treated successfully, treated respectfully. I think we need to be. Why are they concerned? They are worried that we don't have these brand new experimental surprising results, that these wonderful things like string theory and the advanced quantum field theory makes relatively little shed direct light on theories of subatomic particles. Yes, it does shed light on condensed matter physics and aspects of cosmology, that's true, but but for certain people they think that the thing has become too mathematical. Things that I think we are going to see in the future when I think this agenda will play out successfully. I can't guarantee that. I'm not a fortune teller, but I think there are very good grounds for being patient. First of all, I think that we will understand why some of the incredibly complicated calculations that you do in quantum field theory can be done much more simply than are taught in conventional textbooks. That is coming out of this new mathematical approach. Supersymmetry is a new type of symmetry that came out of things called Due models, precursors to string theory, and is an absolute boon to mathematicians, and many of them have told them, and it's also incredibly useful in physics. The problem is that, to the enormous disappointment of physicists, it has not shown up at the Large Hadron Collider. My view is, for what it's worth, because I said you're talking about the future here, and nobody has a, least of all me, on this, but I believe that supersymmetry will show up in some form, right? And it's not been ruled out. That's a really important thing to bear in mind. It's not actually been refuted. It's just been a big surprise that it didn't show up at the energies we now see at the LHC. If that didn't happen, incidentally, then I would regard Dirac's agenda as being seriously damaged. Right? If it really were ruled out, then Dirac's idea that mathematics and physics are really sustaining each other, I would regard that as a very serious thing. But I don't think that's happened yet. We've got a much better understanding of gravity now, courtesy of one Maldacena. I don't have time to go on to that. And there is a very strong belief now, right, among virtually all the theorists at the cutting edge of this, that the understanding we have of space and time, from Newton to Einstein, right, is going to be superseded, and that we really don't understand the very nature of space and time. And much of the motivation from that has come from this very careful mathematical analyses of those theories. What we are seeing, I think, a wonderful thing, is a trend towards an ever greater unity in our understanding of the world. Now, this wouldn't have been believed when I was in the 1970s, but now particle physicists, cosmologists, condensed matter theorists, information theorists are working on the same territory. What we really, really want, of course, is for nature to start shedding some light on this and helping us to advance. My two, take these with a pinch of salt, but nonetheless, I want to at least say them to show that I'm not just being completely whimsical. I think when we're all gone, we're all dead, right? That physics is going to get harder and harder, right, to persuade governments and other whatever else to do these big experiments in cosmology and subatomic particles, and that because of that, it is going to be more and more difficult to persuade them actually to fund these subjects. So I suspect that this mathematical approach to physics is going to become a lot more common. Some people, very, very good people, are very unhappy with it. Right? They're much more happy, much more content when the experiment is setting the cue. But I think in future we're going to see, I hope we see wonderful new experimental things, but I think it's going to be followed by long periods where we're exploiting the mathematics of the theories. And during those decades, physicists will have to focus on the mathematics of the theories. That is my contention. So let me just conclude by thanking you very much for coming. As I said, I can't guarantee you that this is going to be the future of physics, but I do believe that, as I say, at the very basic level, the universe is speaking to us not just through observation, but through mathematics. In short, the universe is speaking to us in stereo. Thank you very much.
back
Following up on Newton and early Einstein, would you say that Bell's theorem is more natural philosophy than it is either math or physics?
Well, I'm not an expert on this, but I would say that that you could. That there's a very strong experimental program on that, and I agree it involves philosophical issues, but it's very, very much something that's amenable to experimental. I don't want to say verification, because that's a word philosophers don't like, but be checked experimentally. So I would very much say that that was a part of or if you like, orthodox physics. I don't see that as something where you have to probe very advanced
But
mathematics.
whether Newton and early Einstein now considered orthodox physics also. So that's not the distinction. The distinction is whether it comes from the math angle or the physics
Yep.
angle or the natural underlying natural
Yes.
philosophy
Yes.
perspective.
Yeah. Okay.
Sure.
You made a convincing case that universe was speaking numbers to the greats like Dirac and Einstein
Yeah.
and Michael Atiyeh and but it is also true that for us simple mortals, when we do our simple things,
Yes.
it is also useful to do it in mathematically conscious, mathematically beautiful way.
Yeah.
So what is the current thinking about interplay of mathematics and physics on much smaller scale? Not for grand theories of everything and so
Well,
on.
I don't think there's any change there. I mean, everybody knows that you have to know some mathematics to be a decent physicist. Right? Everybody knows, and that's continuing to be the case. Perhaps I should have stressed more that the kind of thing I'm talking about, a very small proportion of people that are working, as you rightly say, right, at these frontiers of the subject. For other people, right, for the great majority of physicists and for the great majority of mathematicians, they can work separately and occasionally find things that are useful to each other. I've been talking about the frontiers. Remember, I stressed about
But there is something similar between what happens at the frontier and
Oh yeah. But that's what I've been referring to, and that's exactly what Dirac and Einstein were doing, and they're the people I've been talking about. But certainly, I mean, the idea that there was this mystical relationship, like the torch of mathematics I referred to. I mean, people have spotted that have known that relationship was close. What I think has been particularly novel in the last 50 years is how these two things have been fertilizing each other, as Hermann Weyl said, so directly, right? This I think is really remarkable. The last time that I think that you really saw that in a it would be after Newton had died and you had the continental development of calculus, principle of least action and what have you, where you had physicists and mathematicians, as we would now call them, working alongside each other, right? I mean, your Eulers and your Laplace and his colleagues, they didn't call themselves, they were just people who were doing physics and mathematics. And that's what we're regrowing now.
I would like to share something I heard from David Kazhdan,
Yeah.
who actually explained why mathematicians find physics very useful.
Yeah.
They don't give us a very complementary role. We are supposed to be the mine seppers, because in mathematics many problems have no solution,
Yes.
and you can just work on them and go nowhere.
Yeah.
Now physicists go ahead,
Mm-hmm.
and because they try to connect with nature,
Yep.
they formulate problems where you can go ahead,
Yes.
and therefore it is very fruitful afterwards for the mathematicians
Yes.
to find the path.
Yes.
So we go on the mines and explode from time to time,
Yes.
and they make the progress.
He's laughing. Our friend is laughing here very broadly, knowing how provocative you're being.
I have a question. How much of this is selection bias, though? In the sense that, how do we know that there wasn't Schmeinstein who was working on something else, and it was a terrible idea, and so it didn't work out, and he was trying to use some other type of mathematics, and so we see the successes, and we point to them, we're like, well, that was beautiful mathematics and it worked,
Yes.
but we're missing all the times people applied beautiful mathematics and it failed.
Yes. Well, That's a fair point, and forgive me, I have to keep. Whenever you talk, you know that you're being fanciful, but I would say that it's the old thing about Feynman. The theoretician needs a pen and paper, and a big rubbish bag, right? This is where we need nature. Right? A lot of this stuff, I suspect, will turn out to be fanciful and incorrect, right? People infinitely more talented and accomplished than me, including our friend Nima, will say that the joint constraints, he said this to me so often, I could hear it ringing in my ears, are constantly pushing you towards some direction, right? Unique direction. But even then, you can't deny you can go wrong, and there may be, of course, the obvious thing, which is obviously true, is that it may be that there is some great discovery, analogous to Planck's discovery of the quantum, that is going to just unlock everything. You don't know. That may be the case, right? But for the moment, I think that this, taking the mathematics that comes out of quantum mechanics and relativity, constrained by those two things, is, as Witten says, the best we can do. But you're absolutely right. Some things will certainly be wrong. For example, the Maldacena thing about gravity, right? I mean, I love to tease one about that, because it's not even in real space, this thing, and it is an act of faith that it will have something to do with real space, but we cannot be absolutely certain. I'll be back.
Do you have an opinion as to whether math is created or discovered?
I was hoping you wouldn't ask that question. I hate it because when writing mathematics or such a theory as invented or discovered. Right. Let me just give us a very, very brief summary. I think it's fair to say that most professional mathematicians think they are discovering something, right? When they come up with a new theorem or what have you. It is also true there are a small number of mathematicians and a lot of philosophers that say that it is a human product. Right? Remember, even Dirac, somebody pointed out to me, he says mathematics is again invented by mathematicians. Right? If you ask me my own view, right, it is that we're seeing something discovered. But I'm also a scientist, so I want to know, how do you decide between those two things? Right? But it's a perfectly good question, and indeed there is an analogous question: are the laws of physics discovered or invented? Now on that one, I don't know about you, Neil, that really annoys me when I'm talking to an otherwise blameless philosopher who tells me that basically we're inventing these rules. This drives me quite near to the homicidal act. But that's my shortcoming, and I'm not a violent person. But it's a perfectly reasonable question. Let's have a distinguished opinion. Freeman Dyson, you could always bank on Freeman for a piece of contrarian advice. Is it invented or discovered? Both. That's what he says. He says it's a bit, and I'm serious, he says it's a bit of both. I'm not saying everyone agrees with him, but that's his answer.
There's many arguments. Yeah. This seems like an argument of discovered that's so often appearing in physics.
That's what I think, but yeah.
The fact that there is an agreement between mathematics and physics is also because the mathematics that was developed secretly was developed because of physics. I mean, and we see it even at the sociological level. I mean, if you go to the meetings of the International Mathematical Unions, when Fields medals are given, when you look at the plenary speakers, well, I mean, there is a connection between what was considered interesting by physicists a few years before and what mathematicians do. They will deny it, even under torture, but... So, I mean, Gauss was...
Well, what was he? I mean, he was arguably the greatest ever, but he was doing astronomy and got geography and with his mathematics. It was all over the place.
Historical question. I know that at least in the case of the Nobel in Italy, the first theoretical physicist chair was given only in the 1920s.
Yeah.
Do you know what was the absolute first? The first professorship that was called theoretical physics, not mathematics, not natural philosophy. In Europe, say, when was the first?
To the best of my, I know perhaps a bit too much about this because I studied this a lot. The first person that historians regard as a blue-blooded theoretical physicist was Max Planck, right? And the reason they give for that, incidentally, is that he was the first person. This was in the 1870s, right? Who earned his crust only by doing looking for the laws of nature and having no responsibilities in the laboratory, right? Before then, there might be people, right, who started to do things like that. But I mean, Clausius, for example. Clausius, many people I've heard before said, "Oh, he was a great theoretical physicist." Well, he had a laboratory, right? Now you could argue, well, that's not a very good distinction. You know what I mean? But in my book, which was very carefully read by Helmholtz and other theorists of the 19th century, Planck is the one most people go for, and he was, of course, the person that gave us Einstein, his greatest discovery. It's often said.
So maybe a mathematician and then a physicist.
So a couple of things. One is about Atiyah. So I came into high-dimensional topology, which was my original interest, at a time when Atiyah's work was, was exploding in its influence.
Is it in the 60s?
That's right. Yes, I got my degree in '69. So I very much appreciate him, also him personally, because he was so wonderful to interact with and became such a wonderful friend. I would say that in anticipating the contributions of his influence to four-dimensional topology, which I'd already gotten interested in at that time, but the first I heard about the ideas in which gauge theory could directly was from Atiyah's great collaborator, Singer.
I should have mentioned him.
He
You're
was the
absolutely
first
right.
person who, of course, it's known as the Atiyah Singer index theory
Indeed,
for good reason. Singer is still alive, though not in good shape, unfortunately. And he predicted to me in just a private conversation that it would have a gauge theory and index theory would have a revolutionary impact in four-dimensional topology. He was vague about exactly how, but he clearly had the idea. And that was before Donaldson had done his work and so on. So he clearly was a significant part of that story. I would say. I'll also tell you one funny story, but for good reasons, I will not be willing to disclose who it's about. But one day, I got to know Ed Witten, admired his work and its influence in mathematics, and the mathematical, we keep secret who's going to win the Fields Medal, at least. But there are no, as they say, there are no secrets, right? And so the mathematical grapevine had told me that he was likely to get this prize in mathematics for the influence of in mathematics of his physical work and so on, in pure mathematics. And I ran into an experimental physicist friend, a good friend whose name I'll omit in the story.
Yes.
I won't disclose. And I told him, by the way, the math grapevine is telling me that that Ed Witten is going to, I told my experimentalist is going to win the Fields Medal. Are you touched by the, are you appreciative of the way in which the pure mathematicians are acknowledging physics this way? And my experimental physics pal told me, yes, but not for the reason you think. So I said, well, then why? He said, well, because this way we experimentalists don't have to think of him as a physicist at all.
That's true, and incidentally, that is, I know some very fine, you do too, Neil, very fine, who are not regarded, they just say, well, these people are just living in a kind of, cerebral, mathematical, well, and incidentally, I absolutely stand corrected about Isidore Singer, and he is given prominent billing in my book, so but I thank you for making that point.
Okay, one last question, and then we'll...
As you mentioned, the sort of beauty as a criterion of, scientific truth, it's pretty subjective.
I agree. I agree with that.
How can we be sure, if we don't have that, firm validity of experiment, how can we be sure that we're on the right track?
You can't, and that's why, incidentally, when you hear popular attacks on this kind of physics I've been talking about now, which is drawn back, that it's all beauty driven. Right? I don't actually accept that. I don't actually accept that, and the reason is that I've spoken to dozens of those people, right? And I dare say you people here have spoken to even more, right? They don't keep talking about how beautiful the stuff is, right? That's just a code word, right? For the mathematics is interesting and appealing and what have you. They're not saying, oh, we must have the most beautiful. That is a distortion of the thing, right? But the truth is that beauty thing there is a good popular code. You see what I mean?
Yeah.
That's why I prefer the Dirac line, right, that was interesting. It is interesting to mathematicians, it's interesting to physics, right?
I'm sorry,
It's-
but most of them never talk about experiment either, and observation at all.
Excuse me, I didn't hear
None
that.
of them are talking about experiment and observation at all. Most of them, they're not measuring beauty. They're just like, oh, it's cool that field theory can do this. But they never care about the real world.
Oh, that's not true at all. And I have to say,
Many-
man, that's
many-
really not
many
true.
do not.
They are developing, but they know what they've got to do, right? They are what they are. No. Listen, what the agenda that they're working on is not. They know that the standard model, for example, right, is a wonderfully successful theory. Tick, 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 right? They know that over here you've got general relativity. Tick, 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 tick. They know that in order to actually make progress in theoretical physics, you have to bring those two things together, and that you must test those theories. So please don't ever think that those people, right, are not talking. They are not talking, right? No, hold on.
She's a very well.
They know, right, that ultimately they have to be judged by experiment. That is absolutely true.
Right.
To develop those theories, you have to go through intermediate steps where you have to do these abstract things.
Yeah, that's not how they are advertised. So you have to be careful when you advocate to the general public
Yeah.
that you're talking about, because it puts experiment that has driven Newton. He did great mathematics,
Yeah.
but in physics he wouldn't have been famous if he hadn't had experimental verification. Einstein's theory of general relativity wouldn't be so great if
Yeah.
it was put in the trash can and hadn't had the precession of Mercury or gravitational waves.
Mhm.
So there are several things that by making all this theoretical work and idealizing it, I understand that. I mean, I'm a theoretical physicist, okay? Just to clarify. But you have to not say
Go on.
that experiment, because the way you presented it, it sounded like you were putting not importance in experimental verification.
Oh no! It's vital. If you're mathematics is patterns of ideas. Physics is ultimately grounded in nature. That's what we do, right?
Okay.
Now that does it, right? We've lived through centuries, wonderful stuff like that I'm most comfortable in, of where you're actually dealing directly with experimental data. I'm saying if you really want to actually bring gravity and electromagnetism together, you are forced into that structure, which it turns out, sadly for we humans, a limited lifespan, right, are very high energies that require a lot of ingenuity in order to test them. But if you want to do that by theory, it drives you to that. But please don't think that the people, the best people who will be developing this, are in any way in denial about experiment. I will accept one thing though, right, that it is worrying to me, and I bet you and I will agree on this, right? When you go to talk to a conference of string theorists, right, and they don't actually give a damn whether supersymmetry has been found at CERN. That I find worrying. Right. I also find it worrying, to use Weinberg's phrase that you might hear shortly, when you see physicists who are plainly being seduced by the temptress of mathematics. That's Weinberg's term. Much too good for me. Right. That is true, and that can happen. Right. But I tell you now, if you don't ever say that about Witten, Witten is on the ball.
But Witten is not the field, and we shouldn't. Edward, I know very well. I know how great man he is.
Yeah. Good. Yeah,
But there is a problem of idealizing figures and creating an entire group of people that go on like lemmings.
Yeah.
And doing things like lemmings. So not everyone is Witten, right?
No, that's true.
And he has his mind in the right place, but it creates an entire following of people that go, in a way, following the beauty or whatever you want to call it, or conjectures or whatever that may be, without it completely ignoring. But you see what's happening when you go to string theory conference. Not everyone is with it.
No, I
But you
know that. I
cannot
know
say
it's a danger. I accept that. I accept that.
But then you follow what one person says, then we're not doing physics anymore.
No, you should never.
You should never put a face on a theory.
No.
The theory should be good on its own.
I don't know what you mean by that.
Well, on
Being
that
the-
point, I would argue that we continue this
Yeah, let's do that.
discussion over
Thank you
something.
very much. Hold on a minute, you've been to the plane. You've been on the plane.